Hello everyone. In this session, I'm going to talk about the usage of different kinds of probability distributions in actuarial science. So here the focus is not the theoretical aspects of the various distributions. We will not be dealing with very heavy amount of integrations and calculations which are done in a pen and paper way for finding out the probability distributions of the data. We are using R as a primary tool. So different kinds of packages and different kinds of functions that are available in R to understand the different probability distributions that we commonly use in actuarial sciences. So that is how our entire session is going to go. So as a quick agenda to this session, we'll be having an introduction part wherein we are trying to understand why do we really need to have probability distributions in the actuarial science. What are the different types of probability distributions? You might be knowing the theoretical part. We have continuous distributions, we have discrete distribution, and in some cases we also have a mixed kind of distribution. So that's the basic introduction that we are trying to go with. Then we'll start elaborating the continuous distribution. So we know there are some names already in the continuous distribution, something like a normal, etc. But we'll go more and more systematically trying to understand what are the different distributions that are there and what type of distributions are present in what packages in R. So that's one area we are going to look at. So from the continuous distributions perspective, let's see all the various distributions that we may use in actuarial science and majorly the various purposes for which we may be using them. And for some reason, I know let's say 15 to 20 different distributions, but there is a possibility that my data is not meeting any of these 15-20 distribution. I'm interested in creating a new probability distribution, right? The package is supporting the different packages that we are going to talk of. Let's say they are supporting only 15 to 20 distribution, but I want to create something new which is on the top of these existing 15-20 itself, some kind of manipulation on this 15-20 distribution. I want to create a new distribution altogether. So how do I really go about in R doing that part? So once we are done with the continuous distributions, we'll have our focus on the different discrete distributions that we would be using. Generally, very commonly we'll use the binomial distribution, the negative binomial distribution, the Poisson distribution in various aspects. So we'll try to understand what kind of R functions and R packages are there if I have to handle the discrete distribution. Then we will talk about mixed type, which is continuous for some period, or it's a mixture of continuous as well as discrete. Right, up to a certain value, they follow a continuous distribution, but after that they follow very discrete kind of a distribution. So those are the ones we call as mixed type distribution. So how do I handle the mixed type distributions in R? And if I have to mix two different distributions, let's say I want to mix a gamma distribution with a normal distribution. So how do I really do that and create a new distribution altogether? So these are called as mixture distribution, where I'm mixing two different distributions for some business purpose. So these are the various things I thought I should take up as a part of this session. But let me tell you, more than the theoretical focus here, the focus will not be that heavily onto the theoretical part, integrations, etc. We are primarily looking at using the different packages of R where we can solve problems using the various functions that we are discussing out here. So we know that any actuarial model that we are creating, they have they make any data that we are taking regarding an actuarial model. Let's say we are talking about claims related data, right? We are talking about the mortality related data. So we can think of any kind of such data. The data that we are considering, the data is having some level of assumption regarding the probability distribution. So when I'm talking about the number of claims, okay, there is some assumption regarding the number of claims, Poisson distribution. Or when I'm talking about the claim amount, the severity of the claim, probably somewhere someone says it follows a Weibull distribution or a gamma distribution. So we are making some kind of assumptions regarding the probability distribution of the various elements that we want to track, right? So if you are talking about the claim amount, so we are talking about some kind of a distribution which is applicable only for positive real numbers. So probably a gamma distribution or a Weibull distribution, but definitely not a normal distribution, because normal distribution is applicable even for negative numbers, whereas gamma, Weibull, they are more and more distributions that are applicable only for positive real numbers. Similarly, when I want to model the number of claims, I'll assume that it is some discrete kind of a distribution where the values could be only natural numbers, only counting. I have one claim, two claims, three claims, not 1.23 claims. So every model that we are creating in actuarial science, we are actually making some kind of assumption regarding the probability distribution of that particular variable. So in some cases we are dealing with discrete distributions. So we'll take the probability mass function for that discrete distribution. P of x is nothing but probability that x takes a value equal to x. So I'm not getting into the theoretical aspect. Of course, I expect the basic grounded theory is more comfortable for you, or you may have to refer to some other materials for getting a hold on the theoretical aspect. Then we are talking about in the continuous case, we are defining by the density function, which is given by f of x, which is as good as probability that x takes a value in a very small interval between x and x plus dx. So that's how we differentiate a continuous distribution from a discrete distribution. In some cases, we can have both a continuous part as well as a discrete part. In that case, we will not have a proper density function. If it is a full-fledged continuous distribution, I'll have a density function. But if it is partly continuous and partly discrete, I may not have a proper density function. So in that case, we will not define those kind of distributions by their density function. We will actually use their cumulative distribution function, CDF. So the mixed distributions, we generally define them using their cumulative distribution function. So simply put, discrete distributions, we will define them using the probability mass function. Continuous distributions, we will define them using probability density function. And mixed type of distributions, we will define them generally using the cumulative distribution function f of x, which is probability of x less than or equal to x, which is as good as integrating the probability, summing or integrating the mass function across all the values up to x, right? So these are the three important types of distributions that we are going to look at: the discrete case, the continuous case, and the mixed case. So initially we'll get started with the continuous case. Here, in the continuous case, I want to pitch up two different broad types or families I call them as two different families of distributions under the continuous category. One, we call them as Pearson system of distribution, right? We are taking them as Pearson system of distributions, and the other one we typically call as exponential family of distribution. So of course there is some level of overlap of some distributions falling into both the categories, right? So when we use this Pearson system of distribution, okay, I'll take it up in R, but just giving a brief overview of it. The density function, it actually verifies this particular differential equation, right? 1 by the density function 1 by f of x is the derivative multiplied by the derivative of f of x with respect to x is same as minus of a plus x by c naught plus c1x plus c2x squared. So whatever is the solution that we are getting to this particular to this particular differential equation are typically called as Pearson system of distribution. Just for example, consider this denominator as p of x, right? I'm just giving one simple example. So typically if you say type 0, so if we now I'll talk about a package which has different kinds of Pearson distributions that are packaged into it. This package is called as Pearson DS. PDS are in caps. So we'll talk about our package called Pearson DS, which actually implements 8 different types of Pearson distribution. So they are typically called as type 0 to type 7. 0, 1, 2, 3, 4, 5, 6, 7. So these are type 0 to type 7 kind of distribution. Now the difference is the difference in the values associated with each of these coefficients. So the type 0 distribution, I'll just talk about the type 0. So where C1 equal to C2 equal to 0. So these two are zeros. So it's actually becoming 1 by f of x df of x by dx is equal to minus a plus x by c naught. Now you could very well see this is 1 by f of x df of x is nothing but it's the derivative of log f of x, right? It's the derivative of log f of x because it is nothing but 1 by f of x and df of x by dx. So this is becoming minus of a plus x by c naught. Now I'll take the integral on both the sides, right? So it is becoming log f of x is equal to, now I can take the integration of this, so minus 1 by c naught, and this is becoming a plus x, and the integral of it is again, if I'm taking it as a multiplication by x, or probably I should take it as x by 2, whatever, but that 2 also will go into some constant. Otherwise let me call it as minus 1 by c naught ax minus 1 by c naught x squared by 2. This is the integration part of it, right? And when I'm talking of log, so if I'm taking the log f of x is becoming e to the power of minus this. Now if you see this e to the power of minus this, if I'm seeing all this part, it is looking more like in the normal distribution, if we are seeing e to the power of minus half x minus mu by sigma whole squared. So here also we have a kind of an x squared term. So it looks more similar to this. So this is where we say if C1 and C2 are equal to zeros, this is a type 0 distribution which is called as a normal distribution. So like that, we have different types of distribution. Probably if you see type 1, it's a beta distribution. Type 2, it's called as a symmetric beta distribution. Type 3 is called as gamma. Type 4 is a special distribution where the polynomial function is not having any kind of real roots. Whereas in case of beta distribution, we are talking about one location, one scale. So these are the parameters in the formula that we are going to take. Then Pearson type 5 distribution is called as inverse gamma distribution. Type 6 is generalized beta, otherwise called as scaled F distribution. And type 7 is the student T distribution. So here, when we open the package, if I want to use any of these 8 different distributions, I can simply use one of their 4 functions. Generally, all these have 4 different functions defined. So probably if I'm saying normal, let me open it. That will simplify your understanding. Okay. So first thing, I have to install this package called Pearson DS. So install dot packages Pearson DS. So I am installing this particular package. Okay, this particular package is installed. So let's load this package also using library Pearson DS. Okay, so now we'll take the help first. We'll see what this D Pearson 0, which is a type 0 distribution. D Pearson 0. I want to look at what it is. So the same logic will apply to all. So we are talking about 4 different functions here for every distribution. So there is a D function, right? 4 different prefixes to it. So we have a prefix D for every function, a prefix D, a prefix P, a prefix Q, and a prefix R. If you see here, the D Pearson 0 is the density function. So if you talk about this, these 4 functions, they do these 4 things. The first one gives me the density. Then the second one is the distribution function, which is the cumulative distribution function CDF. The third is giving, so probably the first one is giving me f of x. Then P Pearson 0 is giving me capital F of x, which is nothing but the probability of x less than or equal to x. The third one, Q Pearson, is a quantile. So it is for a particular value of a probability. For a particular probability value, it is trying to compute the value from the density function. So that is what is the Q, which is the quantile function. And R is generating the random numbers for the data of that particular type of distribution. Now if you see, Pearson type 0 is otherwise called as a normal distribution. So I can very well generate the density function for this Pearson distribution by giving a few values. X is a vector of quantiles. So I have to give x as some data. It's a vector. I have to give a mean to that distribution, right? And I have to give a standard deviation to that distribution. And if I have any kind of initial starting values for the parameters of mean and standard deviation, I have to give them. Otherwise, if I just give them here, that should be sufficient. So let me first generate some x. So let's take some x values. So let me take some x values between -5 to +5. So we'll take a sequence -5 to +5, and we'll take it with a gap of 0.1. Right? So we are generating values, or probably we'll take it as 0.01. So very small values. So if I'm looking at x now, so x is containing all the values from -5 to +5 with a gap of 0.01. So overall there are 1000 values of x. Now we'll call it, we'll use different Pearson distributions here. So we'll take Pearson type 0. So we'll call them with something. So let's take y0, d Pearson 0 distribution. D Pearson 0 distribution, initially I have to give the value of x, so I'll give it as x itself, right? X is what I have defined with these values, right? So I'm giving it as x. Then I have to give mean. Mean is equal to, let me take some mean, right? Let's take a mean as 1, and let's take the standard deviation as 2. SD equal to 2. So this is what I have to give. Mean I have to give, SD I have to give. So this has generated my D Pearson. I have given the mean as 1. You can give different kinds of means, different kinds of standard deviation. So this is what has become your Y naught. So you are getting different Y naught values for the different values of X. So directly it is taking those observations, and based on the mean of 1 and standard deviation of 2, it is creating corresponding Y naught values. Now if required, I can very well plot x comma y naught. I'll plot x comma y naught, wherein I'm trying to plot it as a line. So I'll set it type is line instead of plotting the point. I'll try to plot it as a line, right? So let me see what is coming out. So this is a simple plot that I am getting, right? I could see that this is a normal distribution altogether. So I am able to generate a normal distribution through this mechanism as well. Now the other way is I can generate random numbers. So this is where I can use R Pearson 0, right? So let me call x1, wherein I'll generate 1000 random numbers. This is theoretically we are generating the distribution, the density function. The second one is I'll use a random number generation, R Pearson, where I am using n number of observations to be generated. Let's say I want to generate 1000 observations which have a mean of 1. So I'll say mean equal to 1 and SD equal to 2. I want to generate 1000 observations with a mean of 1 and a standard deviation of 2, right? Now on the top of this graph, corresponding to the values of x with a mean of 1, so I want on the top of this, let's say I want to look at the histogram associated with this, right, or the density function. So let me call the line, or let me take a separate plot for this also. Plot x comma x1. Okay, x is having 1001 observations, right? So let me do x1 again by creating 1001 observations. Then let's create plot of x comma x1. So x and x1 is coming out to be like this. So it's fully scattered. But if I want to take the histogram of x1, so this is coming more and more similar to that of a normal distribution itself, right? So I could very well plot the x and y plot, right? X and y, I'm taking a plot like this, and I'll even add on the top of it, let's say I want to add x comma x1. No, it's not x and x1. Yeah, I should not add x and x1 out here, but histogram, right? Probably I can very well add. I should have plotted the histogram first, and then on the top of it I can take the lines, right? Let me plot the histogram first. This is the histogram, and then I'll take the lines where I am talking about x and y naught. So now you could see here, alright, so we are seeing that this is also a histogram, otherwise we'll say par mf row will break this area so that we can understand the things more easily. Mf row equal to C2 comma 2. Now let's plot the plotting of x comma y, which is a line chart, right? This is how it is coming normal, and the other one I want to plot is a random distribution where I'm taking the histogram. So both of them are coming out to be more or less a normally distributed itself. So that is what a Pearson 0 is going to do for us. Similarly, if I want to find out the next one, Pearson 1, let me see what this Pearson 1 distribution is all about. Sorry, I have to give it as Pearson Roman 1. Pearson 1 distribution. So now you could see this is otherwise called as a beta distribution. Again, we have D, P, Q, R kind of stuff. So I can get a density, distribution function, quantile function, and random number generation for the beta distribution. Now if you see the parameters Q, X is, again we can use our same X from -5 to +5. Then we have A and B. So there are two type parameters for this beta distribution, A and B. So I have to give this one shape parameter A, the other shape parameter B. So I am giving two different shape parameters A and B, and I should also give the location parameter and one scale parameter. So these are the different inputs that I am giving. Location parameter of this Pearson type 1 distribution and the scale parameter of this Pearson type 1. So we are actually having four parameters, two shape parameters A and B, one location and one scale kind of parameters. Right? So this is typically the way it is working out. If you look at your A, B's location and scale, lambda is the location parameter, so it is the density function of this is coming out as gamma of A plus B, right? If you want the theory part of it, it is nothing but it is working out as gamma of A plus B divided by gamma of A into gamma of B. Then we also have x minus lambda by s to the power A minus 1, x minus lambda by s to the power A minus 1, into 1 minus of x minus 1 minus of x minus lambda by s to the power b minus 1. See, generally when we take lambda equal to 0 and s equal to 1, we directly write it as x power a minus 1 into 1 minus x to the power b minus 1. Whereas here the location parameter lambda as well as the scale parameter s also would be considered. So we have 4 different parameters out here. I can very well define these 4 different parameters and I can generate different gamma distributions, different beta distributions out here. So let's take our y1, right? Let's take our y1 which is associated with this. So let's see d Pearson 1. Now it requires parameters wise. The first thing is my x, so I'm giving x. Then the next thing is I have to give a value. So let me take some a value here. I'm taking the a value as 1 and b value I'm taking it as 2. Similarly, I could take my location parameter as 1 and the scale parameter I'll take it as 2. Now based on this I get another distribution created y1. So if I want I can very well plot x comma y1 type equal to L. The line chart I can very well plot. So this is how this is coming out, right? You could see the distribution is coming out in this way, A, B. Now the way I keep changing the x's, so this is not a normal distribution, right? You could see a lot of difference out here. We have a value equal to 1, b value equal to 2, and again we also have the location parameter as 1, which is where the mean is actually coming out. You could see the location parameter is coming out to be 1 and scale parameter is 2. Now we can very well change the parameter values, all these 4 parameters, and we can very well get different kinds of shapes for this beta distribution. Now the same logic goes when I am trying out for the beta 2 distribution, Pearson 2 distribution. Now, so this is how you can actually practice all the distribution. So the Pearson 2 is otherwise called as a symmetric beta distribution. So instead of 2 parameters A and B, so if A and B are actually the same, instead of 2 parameters A and B, I'll have only 1 parameter here. That is what we could see in the notes out here. It's containing only A. So that is why we are calling it as a symmetric beta distribution. So if I have to quickly look at y2 out here, all I make a change to this y2 is I'll take only one value of A. Let's say let me take it as 1 itself. The B part I'll take it out. That's it. Location, scale I can very well maintain. And this is what I am calling as D Pearson 2 distribution. So the density function associated with a Pearson 2 distribution. And now if I want to plot this particular distribution, I will plot y2. So this is how the symmetric, when I have taken A and B, both of them as ones, this is how I am getting the graph, right? So it's a beta distribution, symmetric beta distribution. This is how the shapes of the symmetric beta are going to come out. Now when we really work out with our data, we may have to see which distribution is more appropriately fitting this kind of data. So the fitting distributions to a particular data will take it up as a separate understanding. But here we can see the different such kind of distributions that are there as a part of this model itself. Now similarly I can very well go ahead with the y3. The third distribution, the Pearson type 3 distribution. Let's see what is this type 3 distribution. Right, when I'm typing the type 3, it's actually a gamma distribution. So it requires a shape parameter, a location parameter, and a scale parameter. Three things it requires. So what we can do is, the scale we can still keep it as 2. Location we can still keep it as 1. Right, location and scale. Now I have to add a shape parameter. So instead of a equal to 1, let me directly set shape equal to 1. Right, let me just set shape equal to 1. This becomes a gamma distribution. And now when I am trying to plot this particular gamma distribution, which is y3, I get it more like this. So it looks more and more extreme valued, and on the other side you could see it is defined only for the positive values. For the negative values, it's coming out to be undefined. Right, it's coming out on the horizontal axis itself. So this is where we are seeing that the gamma distribution is more and more associated with the positive values itself. Now moving on to the fourth one. Now for all these things you could very well plan out the corresponding random values. We could get the probability distribution function, or even the quantile functions as well. So the 4 is a special type of a distribution which requires the m. M is the first shape parameter, so we are giving the first shape parameter. Nu is another one, which is the second shape parameter, which is the measure of skewness here. So we have two shape parameters in m and nu, and we have one location parameter and one scale parameter. In this particular distribution, we are talking about two different shape parameters. Probably if you remember the first beta that we have talked about, there also we had two shape parameters, but here the difference is the second shape parameter is a measure of skewness of this particular distribution. So I can very well use the same 4 which I have used for the beta distribution. So let me use y1 itself, right, and I'll just make small changes to it. I'll call this y4. So instead of a, I'll set m equal to 1. Instead of b, I'll set the second shape parameter nu equal to 2. Location and scale, I'll keep them as it is. Okay, it should be 4. Let me give it as Pearson type 4 distribution. Okay, so based on this, if I want to plot 4, so let me say I want to plot y4. This is how the y4 is coming out, all remaining the same. But when I had taken y1, it was coming like this. So the shapes are entirely different because all remaining the same. In case of Pearson type 1 beta distribution, the b was a parameter, whereas here the b is equal to the skewness of that particular distribution. So this is how you can actually play around different kinds of distribution. We have Pearson, the same way you can go ahead, right? I think I don't need to keep repeating the stuff. The Pearson type 5 is an inverse gamma distribution. Let's try Pearson type 5, which requires one shape, one location, and one scale. So I'll take one shape, one location, and one scale parameter. So probably similar to y3, right? I'll take something similar to y3, all else remaining the same. Let me call it as Pearson type 5. And now I can very well plot the y5, oh y3 only, right? Okay. So this is how the Pearson type 5 distribution is going to come out. Type 3 is gamma. Type 5 is coming out to be inverse gamma distribution. So we have different such kind of distributions which we can use. I'll tell you at later point how do I really use for my specific data which distribution it is working out with. Pearson 6 is a beta prime distribution which requires two different shape parameters A and B, just like a beta distribution here, but this is more generalized beta kind of distribution. So two shape parameters A and B are required, and one location and one scale parameter are required. So this also, if you see, the equation is more or less similar. The density function is looking more or less similar. The only difference here being to the power of minus a minus b. This is because it's a generalized kind of a beta distribution. Similarly, I can take the D Pearson 7 kind of a distribution, which is more similar to your T distribution, the student T distribution. So it requires degrees of freedom, the location, and the scale parameters. So these are the three things that it requires. So what we can actually do is we can actually plot all these 7 in one single graph and see how the distribution is typically going to come. So let me try one thing. Let me make this bigger. Our MF row is C1 comma 1. So I am making it a bigger one single itself. So X, anyhow we have taken the values from minus 5 to plus 5 incremented by 0.01. Y0, let me call it as D Pearson 0, wherein some inputs are being taken, X and the Y value. So the two parameters are required. So let me set them as, so let me set the parameters 0 and 1. Right? Similarly, I need Y1. Y1 is my beta distribution which requires 4 parameters. So D Pearson 1. Let me take X and parameters 1, 2, 3, 4. I'll take these 4 values as the 4 different parameters. First two are the two shape parameters. Then I have one location and one scale parameter. So this is what I am taking. Right, location parameter, actually let me take it as 0. So then probably I'll take this as 3. Okay, so then I'll set y2, which is a symmetric beta, right, which is D Pearson 2. So I require to give only one value of A. So let me give 1, and I have one location parameter 0 and a scale parameter. Let me take the scale parameter as 3 itself. Then I have y3, which is my gamma distribution. I'll say D Pearson 3 X. This also requires one shape parameter, one location, and one scale parameter. So I'll take it as 103 itself, shape, location, and scale. Right, and y4 also let me do the same. Y4 is a special distribution which is more and more similar to I can take y4 D Pearson, which requires 4 parameters here. So I'll take them as x comma 1 2 0 3, more similar to my y1 itself. Then y5 is your inverse gamma distribution. So I can give the similar kind of numbers associated with the gamma for it. So D Pearson 5, I'll give the same inputs as D Pearson 3 because this is gamma inverse gamma distribution. So I'll take y6 as d Pearson 6, which is a generalized beta distribution. So whatever the input that was given to the beta distribution, I'll consider the same input for this as well. And when it comes to y7, where I'm looking at the t distribution, I'll take it as d Pearson 7, wherein I'm considering the degrees of freedom. Let's say I'm considering 3 degrees of freedom, and I have a location and a scale. So location is 0, scale is 3. So let's say we have these different kinds of distributions that we want to plot in one single chart. So initially let me plot one of them. So I'll plot x comma y naught. The first one I want to plot, wherein I want to plot it as a line. So I'm setting it as type equal to L. Now I want to set the limits, right? I want to set the limits based on the range of all the y values. Otherwise, sometimes some of the graphs could go out of the chart. So this is where I say y limit, let it be considered based on the range that is associated with all my values, y0, y1, y2, y3. So based on the range associated with all, so consider whichever is the one that is having the highest possible range, take that as the range of this particular graph. Right? Take the y-axis limits based on that particular range, rather than just considering y0's range and doing a plot. Take the range across from y0, y1, so on up to y7. Okay, so this is how my y0 is plotted, right? This is how the y0 is plotted. Now I can very well take the y1, y2, so on. So let me take lines, let me add the lines to it, where I am considering x comma y1, right? I am considering x comma y1, color equal to red. So this is how the y1 is coming out. Now you could see the way the shape is changing. Similarly, I can add the y2 to the same graph, wherein I'll make it green. So this is how my y2 is going to come out. Then I'm adding y3, which is the gamma distribution, where we can make it blue. Okay, so this is how the gamma is coming up, where the location for all of them is the same 0. But if you see, the gamma is becoming more and more extreme, right? The tail is much fatter out here. Similarly, when I am considering y4, which is that special distribution, if I take it with orange, so this is how the y4 is coming. The special distribution, you could see that there is a lot of tail towards the left compared to the right. Then we are talking about a y5, which is an inverse gamma distribution, which I am looking with a pink. So the inverse gamma is looking like probably let me do it with a different color, purple. So the inverse gamma is coming out like this, which is also defined only for positive, but you could see there is a kind of an inversion with respect to the gamma distribution out there. So that's the inverse gamma. The generalized beta, where I'll call it as dark green. So the generalized beta is coming slightly more curved out here. The red one is the beta. This is the generalized beta. So you could see it's more and more curved kind of stuff rather than a dropped straight line. So that's how you could see almost all of them. Similarly, the T we can give some other color. I'll give maroon. So this is how the T is coming, just like a normal, but it is more and more flatter compared to a normal, but it is having more and more fatter tail. So you could see that with the similar kind of values that we have given, almost the location parameters being 0 in almost all the cases, the scale parameters being the same, just by changing the shape of the distribution, the shape parameters of the distribution, we could see different kinds of shapes that are coming out altogether, and that is what we really need to be comfortable with. So these are the different first set of distributions that we really need to be comfortable with, right? These are called as Pearson category of distribution, and we can use that Pearson DS package, and using them we can very well generate the distribution, the density functions, the probability distribution function, the cumulative distribution functions, and as well as the random numbers associated with each of these four types of distribution. Right? Now, moving on to the next set of distribution. So, under the Pearson DS, we have looked at some of the common distributions like the beta distribution, the symmetric beta, the normal, the gamma distribution, right? Inverse gamma, generalized beta, and even the T distribution. So this generalized beta otherwise is called as a scaled F distribution as well. So we have looked at all these distributions in the Pearson DS package. Now, the other important family of distributions that we are looking at here is the exponential family of distributions, whose density function can be written like this. This is the theoretical aspect. Wherever I can write f of x as e to the power of sigma ajx alpha j theta plus b of x plus beta of theta. So whenever I am able to write in this form, this is what we call as exponential family of distribution. So just for example, I'll talk about the basic exponential distribution. We know for an exponential distribution, f of x is nothing but lambda e power minus lambda x. Right? Now, how do I write it in this exponential family? Now, within this, see if you set d equal to 1. So, it is like e to the power of 1 to 1. A of x. So, instead of this whole thing, we are calling it as x. And alpha of x, we are taking it as a constant lambda. So, it is becoming x lambda plus b of x is being taken as 0. So, this part does not exist at all. And beta of lambda is nothing but log lambda. So overall it is coming out as f of x equal to x lambda e to the power of x lambda plus log lambda. This is what is coming out. So now let's expand e to the power of lambda x, and this is e to the power of log lambda. So this is nothing but lambda e to the power of lambda x. So this is what we are calling as the exponential family distribution, which is the exponential distribution altogether. Similarly, by setting some other things, so we can convert, we can very well rewrite this into a normal distribution form as well. So again, there are so many distributions in the real world. which belong to this exponential family of distribution, which can very well be handled by doing some kind of modifications to the generalized terms A, alpha, B, beta kind of term. By making some kind of changes to them, we can very well convert them into an appropriate distribution. Now here, what we understand is almost all these distributions can very well be used. A beta distribution, Cauchy distribution, chi-squared, exponential distribution, F distribution, gamma distribution, logistic, log normal, normal, T, uniform, Weibull. So there are many such kind of distributions that we can very comfortably use, which talk about all these are coming under the exponential family of distributions, right? We can very well write the density functions for all these types of distributions in this particular form. With small workout, we should be able to understand how we can write all these things in this particular form. Now, all these things are present even as a part of the base package of R, or there are a few important sophisticated specialized packages in R which are exclusively dealing with various actuarial distributions. We have different kinds of packages dealing with actuarial distributions. I'll talk about them in the next slide. But just to give you an input, Actuar is the name of a package which contains quite a good number of actuarial distributions, right? But yes, so let's see, these are all present as a part of the base package itself. And as we have discussed earlier also, all of them have these four implementations. We talk about the density function prefix. So when I say d norm, it's a normal distribution, right? Or probably when I say dl norm, it is log normal distribution, the density function of that particular distribution. Then if I put p as a prefix to this, it is called as the probability distribution function, which is the cumulative distribution function associated with this. If I put a prefix q, it is associated with the quantile, and when I am putting R, it is more associated with the random number which is following, right, generation of a random number following this particular distribution. So we can very well experiment different kinds of distribution, right? So let's say quickly let's try it out. Let me take the R. So here I want to try out different kinds of let's say a gamma distribution I want to try. So we want d gamma, correct? We want d gamma. So let me say what this d gamma function typically contains. You see here again density distribution, it's there as a part of the base stats package itself. It gives me density, distribution, quantile and random number for the gamma distribution, where a shape and a scale are provided, right? I can provide a shape parameter and I can provide a scale parameter, and based on that I can very well get my gamma distribution executed, right? So once I give the rate parameter, the scale parameter is automatically 1 by rate itself. So I'll give the shape parameter as well as the rate parameter, and I can very well get the d gamma, right? So let me say x is, I'm taking a sequence from -5 to +5 increment by 0.01. Then y, I'll take it as d gamma, wherein I'm taking x as the input, the shape parameter let me take it as 2, and rate parameter, let me take it as 3. So I'll get the y value. I can very well plot x comma y, and let me plot it as type as a line. So we are getting plot x comma y, and this is how I see that this particular gamma function with a shape of 2 and a rate of 3. Now if I change, let's say y, instead of rate 3, let me make it to 4. And now if I try plotting the same, so this is how the graph comes out. But let's say if I am setting the shape parameter as 0.5 and now trying to do the plot, I get it in a slightly different way. So depending on the shape and the rate parameters, I get different values. Similarly, if I am going with P gamma is giving me the cumulative distribution function, right? So probably I can talk about, yeah, let's use y1 as P gamma. So instead of density, it is giving me cumulative distribution. So we'll take x, the same shape equal to 2 and rate equal to 3. So what happens is, for the last one, I'll get the cumulative value as 1. For the first one, I'll get it as 0. So let's try plotting x comma y1, wherein the type I am setting it as L. So it starts at 0, it goes up to 1. So this is how the cumulative distribution function is coming, which we get through the plot function. And now let's say I want to find out what is the typical value of x, let's say corresponding to 50%, corresponding to a probability of 0.5, what is the corresponding value of x? This is where I can use the q gamma. So if I say y2 where I am using q gamma, again let's say I want the probability associated with 0.5, 50%, which is like a median value for me. For this data it's like a median for me. So wherein I want shape equal to 2 and rate equal to 3. So if I look at y2, it says 0.5594. It is at this particular value I get the cumulative distribution value equal to 50%. So that's how. And if I want some random set of values, y3, let's say I'm using r gamma, I want to generate some 1000 numbers with shape equal to 2 and rate equal to 3. So this is like data is generated now. I have 1000 elements which are following a gamma distribution with a shape of 2 and a rate of 3. And to understand, if I try to plot the histogram of this y3, the shape would be more or less similar to what we have theoretically visualized using the d gamma function. Or just to test it out, let me see the median of y3. It should be more or less similar to this value that we have got. So 0.57. Randomly, if I have generated the values, I got the median as 0.57. Theoretically, when we have computed the same, it worked out to be 0.55. So that's how you can very well visualize the 4 functions associated with each of the distributions. So you can try out for different distributions, the D, the P, the Q and the R functions. And as I have already indicated to you, so specifically to actuarial sciences, we have a big list of distributions that we generally use, and in some cases we may have to create our own kind of distributions as well. So to get a big list of distributions, I suggest that we use this Actuar package. So let's install this Actuar package. So I'll say install.packages Actuar. Okay, it's already there on my system. So I have the Actuar package already loaded. So you can use even active distance, which is the actuarial distributions kind of a package as well. So you can read through the documentation associated with each of these packages to understand the different kinds of distributions that are typically supported. Right, so probably let's look at the Actuar. So let me put question mark and Actuar. Okay, so we have Actuar as the name of the package out here. You could get complete, this is just initial uh, okay, the Actuar package. Okay, let me just look at. Let's take one function directly, right? So this is where let's take d gamma, which is there from the Actuar. No, Actuar d gamma is there in the stats package itself. We'll take up. The best thing is let's take up these extra functions, right? I'll get the moments if I have the Actuar package. Apart from these four, D, P, Q, R, I can also execute M. M is I am getting the raw moments directly. So let's try M gamma, right? Let me call M gamma. So let me put a question mark saying M gamma. So it says it's in the Actuar package, raw moments, limited moments, and moment generating functions. These are the three. So if I am putting M gamma, I will get the raw moments. And if I am putting leverage gamma, limited gamma, LEV gamma, I am getting the limit of the loss variable, which is the limited moment. And I can also get the MGF, moment generating function, if I am using MGF gamma as a function. So if you see, the kth raw moment is nothing but expected value of x to the power of k. Kth limited moment is at some particular limit value d is nothing but expected value of minimum of x comma d to the power k. So I don't need to take x always. So whichever is the minimum value between x and d, I'll take that to the power k. So typically in my reinsurance kind of scenarios, I can very well take the help of this limited moment. And the moment generating function is nothing but expected value of e to the power of dx. So we can get all those three. So what we can do is, let's say if I want the M gamma, I just need to give the order of the moment. Let's say I want the mean of a gamma distribution, right? So if I say M gamma and if I put order 1, order 1 is the first order expected value of X, which is the mean. Order equal to 1, shape equal to 2, rate equal to 3. Now we know the formula, right? Alpha by beta. So we know the formula, but we can very well check out. So it is coming out alpha by beta 2 by 3. The first moment is coming out as 2 by 3 for this gamma distribution. If I say second moment, it is expected value of x squared. And we know the first moment expected value of x is alpha by beta variance of x is alpha by beta squared, right? So from here we know that the variance is nothing but expected value of x squared minus expected value of x whole squared. So this is alpha by beta squared. So from here you can find out expected value of x squared is nothing but alpha by beta squared plus alpha squared by beta squared. So which is making it alpha into 1 plus alpha by beta squared. That is expected value of x squared. So now anyhow we have 2 and 3. 2 into 3 by 3 squared, which is what is working out to 2 by 3 only. So let's take out the second order. In this case, even the second order is working out to be the same. That is what is our calculation is also saying. So you can very well get different kinds of distributions, not just the gamma. You can try out different such kind of distributions using all of them, and you could also get the moment generating function as well. MGF, I have to give the x, which is a numeric vector, the shape and the rate, and based on that I get the moment generating function associated with this particular gamma distribution, right? Probably one way to check out MGF gamma, right? I'm taking MGF, so I'm taking a single valued vector 2, and for which I'm having shape equal to 2, rate equal to 3. So the MGF is coming out, the moment generating function for this x value of 2 is coming out to be 9. So that's how I am getting all these computations being performed. The Actuarial package contains these 3 additional prefixes as well, along with your D, P and Q and R kind of functions also. Now, in some cases, it so happens that in spite of having so many such kind of ready-made distributions, it is very much possible that none of these distributions typically match our data, right? Even if I try to fit any of these distributions to the data, it might so happen that many of these or any of these distributions may not fit the data appropriately. So in that case, it is very much possible that we may have to transform. We may have to create a new distributions altogether. So by doing the transformations of x. So it's as good as saying, instead of finding out the gamma distribution with respect to x, I want to find out the gamma distribution, let's say associated with x squared, or I want the gamma distribution associated with log x. So there are different kinds of transformations. I may want it as x plus or minus some constant. Scaling can be done. Power can be used, x power alpha. Inverse, of course, this is also same as x to the power of minus 1. Logarithm, gamma function for log x, gamma function for e power x. So I may be interested in finding out for the different kinds of transformations. I am more interested in finding out the gamma function. Instead of taking the gamma function of x, I want to take the gamma, how the gamma function looks for x plus 1. Right, instead of taking x, I want to go with x plus 1. So in this case, there are two ways. One, we can write our own custom functions. So if I am talking about a gamma distribution, if I want, see, f of x is the density function with respect to x. But if I want the density function with respect to x squared, right, if I want the density, gamma density function with respect to x, it is f of x. But if I want the density function of x squared, we have a different way. If you remember, so you take y equal to x square, then take x is nothing but square root of y. So now once you have taken this x as square root of y, now take it as f of g inverse. So now this is nothing but g of x. So you are getting x is nothing but g inverse of y. So you are taking directly f of g inverse of y. So if you want it, so you can very well take as f of square root of x, and you know that the derivative of g inverse of y is nothing but 1 by 2 root y. 1 by 2 or 1 by 2 root x. So you can very well take it as 1 by 2 root x into f of square root of x. Now this is a function that you can very well write theoretically, and you can very well generate the values associated with the function of x. So let's try it out, right? So let me create one single function, let's say f, which is the original function itself. So let me take a function of x. This is a function of x which is the d gamma, which is the probability density function of x with the shape equal to 2 and rate equal to 3. This is the density function associated with x. Now I want the density function associated with x squared. So this is where I'll again take it as the function of x, but I will take f as the base. Now within this f, it is f of, this is the transformation, f of square root of x. So I'll take it as f of square root of x, right? I'm taking it as f of square root of x divided by 2 into square root of x. 2 into square root of x. So this is what is becoming my f1. So f of x is the d gamma. Now instead of f, I am taking the transformed because I want to find out the gamma associated with x squared and come out with a new function altogether. So that's how I have taken these two. So instead of x, now I want to look at it x squared, and for x squared this is what I can generate. Now let's look at x, where I am taking the values from -5 to +5 incremented by 0.01. So based on that, let me plot x comma f of x. Right, I'll plot these two things wherein I'm setting the type equal to L. I'm plotting these two things type equal to L, wherein I'll set my y limit also based on the range associated with, so here I am not computed, so because I have not computed the range, let's leave it as it is. Right, so let me set the values as it is. I am plotting x and f of x. Okay, so this is how I am getting the values of x and f of x. But let me add line wherein x comma f1 of x, let me take up. Right, I'll lines, and I'll put a color to this as red. So this is how the f1 of x is going to come up. Right, of course for negative values there is no possibility, so that's the reason it did not start anywhere here. That is where the not a numbers are typically produced. But what you could see is from here the curve is slightly different from the typical gamma of x kind of a curve. So that's how you can very well play around with different kinds of functions. And the same way, you could randomly generate the values also. Even you could follow the random number mechanism. Initially, you can generate, right? You can generate the x's. Initially, you can generate the x's as r gamma, some thousand numbers. Let's generate, right? Let's generate some thousand numbers where shape parameter equal to 2, rate parameter equal to 3. So then if required, we can very well plot the density of, we'll plot the density of x, right? So the when I'm taking a random values, this is how the gamma function is typically coming out. So these are the x values. Now what I will do, I'll take x1, right, which is nothing but the square of, I'll take the square of x because I'm plotting for x squared, right? So I'll take it as the square of x. That is what I'm calling as x1. Now I want to plot the lines wherein I'm talking of the density of x1. I'm taking the density of x1 and I'm taking color equal to red. So this is from the actual data. So this is how the density is coming out. If I'm taking a random numbers altogether, this is how my graph is coming out for the gamma of x as well as the gamma of x squared. So we can very well do the transformations of different functions of the random variable. So instead of taking the random variable as x, I can take the random variable as x squared or square root of x or 1 by x, whatever. But simple thing is take an inverse of it, right? If I am talking about gamma of x, but if I want gamma of x squared, first take y equal to f of x equal to x squared. Based on that, you take x is nothing but f inverse of y is equal to square root of y. So now you take the derivative, so you take it as f of this, so which is becoming f of square root of x, and you take the derivative of that, which is making 1 by 2 root x. So this is what is the new function for me, which would execute the gamma of x squared. I can get the gamma of x squared exactly by writing a function with respect to x. With this, so the x is the function of x is d gamma function. The function of x squared is coming out as the same f of 1 by f of square root of x into 1 by 2 root x. So that's how I can very well change the functions, or I can take random numbers, whatever it is. Based on that, I can very well generate new probability distributions from the existing distributions. Then we know that there are so many distributions that are used in actuarial science. We can use uniform distribution for generating various random numbers. We use uniform distribution, right? If I want to generate random numbers following a beta distribution, or if I want to generate random numbers following a gamma distribution, it's very much essential that I first generate random numbers using the uniform distribution, and after that apply the necessary transformation to generate the random numbers following some other type of distribution. So similarly, we are using the beta distribution. We'll use triangular distribution. Again, different kinds. Now theoretically, I don't want to get into each of these aspects, but it is very possible that we use almost all these kinds of distributions in actuarial sciences. So we have different distributions coming from the gamma family, right? We have a transformed gamma distribution, which is a generalized distribution with parameters alpha, tau and lambda. We have an inverse transform gamma distribution. So within this, by setting tau equal to 1 and only between alpha and lambda, it becomes a gamma distribution. If alpha is set equal to 1, having only tau and lambda, it is Weibull distribution. Now, if both alpha is set to 1 in a gamma distribution and tau is set to 1 in a Weibull, I can very well convert both of them into exponential. In gamma, by setting alpha equal to 1, it becomes an exponential distribution. In a Weibull, by setting tau equal to 1, it becomes exponential. So we can very well convert one to other among these category of distributions. Similarly, the same logic, you have inverse gamma, inverse Weibull, inverse exponential kind of functions. So at different points, we would be using all these kinds of distributions as a part of our actuarial models. Similarly, we have a big beta family of distributions with alpha, gamma, tau and theta. Again, if tau is set to 1, where the inputs are only alpha, gamma and theta, it becomes a Burr distribution. If alpha is set to 1 with only gamma, tau and theta, it becomes an inverse Burr distribution. Now if gamma is set to 1 with alpha, tau and theta, it becomes a generalized Pareto distribution. So all these are coming from the beta family of distributions itself. Now within the Burr distribution again, if you have gamma and alpha, both of them being equal, right? If gamma and alpha, both of them are equal, it is typically called as paralogistic distribution. So because we have both alpha and gamma as equal, we don't need to define them separately. It becomes a paralogistic distribution. But instead of alpha being same as gamma, if it becomes 1, it becomes a log logistic distribution. And instead of gamma being equal to alpha, if gamma becomes 1, it becomes a Pareto distribution. Now you could see you have all these kinds of distributions coming from the beta distribution family. So all these distributions in some form or the other, we are going to use them for various calculation purposes on the actuarial data. So we have to be comfortable using all these distributions, having an understanding of all these distributions. But to be clear, we can very well get all these distributions as a part of our package, right? Let's see if I'm talking about Pareto, right? D Pareto. So it's there as a part of the Actuar package. All I need to give is the X, the shape and the scale parameters. So we have two parameters, right, as a part of Pareto, alpha and theta. So I have to give the rate and the scale, the shape and the scale parameters to typically get the density function associated with a Pareto distribution, right? I can get the density function, and M Pareto is giving me the moments associated with the Pareto distribution. So if I say M Pareto, right, let's say the mean I want for a Pareto distribution, I'll say 1. Then I have to give the shape as well as the scale parameter. So you say shape is 2 and you say scale equal to 3. So we are getting the Pareto distributions first order moment, which is the mean, which is working out to be equal to 3. So you can compare them with the theoretical formulas. So that's how we can simplify our understanding of the subject regarding the different distribution. So let's say I want, right, we are having all these different Pareto distribution, different kinds of distributions that are working out for us. And almost all the distributions here, let's say I want log logistic, have to put this in double quotes. So you see here we have log logistic. Again, DL logis. If I'm going with DL logis, I get the log logistic distribution. Again, I have the D prefix, P prefix, Q prefix, R, M, and LEV. So you could see that almost a big chunk of distributions are defined as a part of this Actuar package. So executing things in the Actuar package, trying out the fitment of a particular distribution to a data will simplify our understanding of the entire process as well. So that's the reason for actuaries, the Actuar package is one of the most important and heavily used kind of distribution. Alright. Now, having got a fair amount of idea regarding the continuous distributions, now let's move on to our next topic of discussion, which is the discrete distribution. Again, the while the continuous distributions are verifying a differential equation, here we say the set of distributions which are verifying probability of x equal to k plus 1 divided by the probability of x equal to k works out as a plus bk. Those kind of distributions are typically considered as discrete distribution. Now if you set, just for example, Poisson distribution, set a equal to 0, b equal to lambda. So we are saying probability of x equal to k plus 1 divided by probability of x equal to k. It is coming out to a plus a is 0 here, b is lambda, so it comes out as lambda by k. Just let's test it out. What is the density function associated with Poisson distribution? F of x is nothing but e power minus lambda, lambda per x by x factorial, right? So let's use that here for this example. E power minus lambda, lambda power k plus 1 divided by k plus 1 factorial. This is the probability of x equal to k plus 1. Now we'll take probability of x equal to k. E power minus lambda, lambda per k divided by k factorial. So if I am simplifying this, so this is nothing but k plus 1 and this is coming out to lambda. So overall it is coming out as lambda by k plus 1. Right? So you can very well simplify the stuff. You can very well simplify the stuff this way, where we can express one in form of the other. Now that's how we want all the kinds of distributions which can verify this kind of a formula. We are trying to call them as discrete distribution. The same logic goes with negative binomial and other discrete distributions as well. Now, just like the way we had R functions talking about the D, the P, the Q and R for continuous distribution, we also have similar kind of things associated with discrete as well. We have D poise, we have P poise. Similarly, we have D binom, R binom, or even Rn binom, which is the negative binomial. Again, the same set of things. So we will get the density associated with a particular set of values when we are going with the D. So here in case of density for a discrete distribution is nothing but it's the mass function. Similarly, we have cumulative distribution functions. We can get the quantile function as well as we can get the random numbers following the particular distributions as well. So these are some of the important points that we need to keep in mind when we are working with the discrete distribution. Now, again, in this case also, we can very well do the transformations to get some new distributions of our choice. If I want, I can very well do instead of x, we can go with x plus 1, right? We can do a scaling, we can do a additive versus subtractive kind of stuff. So all these kinds of transformations also can very well be performed. In all these cases, the simple stuff is you generate random numbers going with these each of these distributions, and probably try computing the graph and various other things associated with them. Now, moving on to the next one, which we are calling as the mixed type distribution. So in the mixed type distribution, they are actually neither continuous nor discrete. So up to a certain point, they are continuous, and after that they become discrete. So they have discontinuities, which is what is talking about their discrete part, and there is also a continuous part. So if I look at their density, a distribution function, it looks like this. So there is a p probability that the distribution function will be 1 itself. Let's say for all x that is greater than or equal to 0. So the distribution function will have a value of 1. And in all other cases, so which is a 1 minus p as a probability, it follows a gamma distribution. Gamma distribution with alpha and lambda. So similarly, this is called as the zero modified gamma, because at 0 we are having the density of the distribution function will take a value of 1, and at all other places where the probability is 1 minus p, it follows a different distribution altogether. Similarly, you see here one modified beta distribution. So there is a probability q where the distribution value is equal to 1, especially for x greater than or equal to 1, right? So from 1 onward, so it becomes the distribution function will be more like this. So the moment the value comes to 1 and above 1, the distribution function is 1 itself, but below 1 it is actually following a kind of it's following a kind of gamma distribution or a beta distribution. So these kind of functions, so until you typically meet up a particular value, it is following a continuous distribution, but after that it is becoming a kind of a constant. So typical applications, we are talking about the destruction rate models, wherein I am looking at the percentage of loss, and D is defined as the maximum loss, and L is typically being looked at as the actual loss amount that has occurred. So this will typically be a proportion of the total loss, but it cannot happen that L is greater than D at any point. So this is where we are restricting that the maximum loss can be, the percentage is only 1, but below 1 we are saying that it follows a kind of a continuous distribution. So x will be there in the interval 0 to 1. Maximum mass is at 1, where the whole structure is destroyed, but below that it need not be linear. It may follow a gamma distribution or a beta distribution or some other kind of a distribution altogether. So it is in these cases we are calling these kind of distributions as mixed distribution, because up to a certain point they are continuous and beyond a certain point they are discrete. In this case, the best way to handle them is create your own functions. Right? I'll say for the same example. So if I say for 1 and above, for the values of x which are 1 and above, let's say the distribution is for the values of x 1 and above, the distribution function value is equal to 1, and for values below 1, so if I have this situation for x is greater than or equal to 1, f of x comes out to be 1, and for x value less than 1, during where x is less than 1, let's say it follows a beta distribution. And if I have to model such kind of a relationship, this is where we are calling as mixed type, right? And this is called as one modified beta, because at point x equal to 1, I am not using a beta, I am modifying the beta. So this is where we will create a new function here. Let's say d beta 1 modified, right? I am creating a d beta 1 modified, which is a function of x. Along with that, I have to specify what is the probability that x will be greater than or equal to 1. So this is where I have to set some probability value, which talks about what is the probability that x is greater than or equal to 1. And beta function requires two different parameters, two shape parameters a and b. So I am defining with all these things a d beta om function. So what we say here is when x equal to 1, right, we'll take it as x equal to 1 multiplied by the prop. What is the probability that x is going equal to 1? And along with that, I'll take it as 1 minus prop, the remaining part of it, where x is not equal to 1, right? I am taking x is not equal to 1. In that case, it is nothing but it's a d beta distribution. So it's a d beta containing x and a comma b. So this is what is the name of the function that we are providing. Right? So we are defining a simple function wherein this is called a one modified beta function. Right? So we can very well define for some parameter values a and b to get a good understanding. So let me just try out. X is having the values, right? X is having the values from minus 5 to 5 with an increment of 0.01. Y I will take it as d beta of x, where a equal to 2 and b equal to 3. Okay, I need smaller values. So a is 0.2. Oh, let me give shape. Right, let me not call them as a and b. Let me just give 2 comma 3, where I am using the shape and the rate parameters. So this is what is coming out as y. So let me plot x comma y type equal to L. So this is how the beta distribution with parameters 2 and 3 is typically coming out. But then if I use d beta, right, let me call y1 as d beta om, where we are doing a 1 modified for the same x 2 3. Oh, I require probability as well. So let me set probability is 0.1. Right, I'll set x equal to the probability is 0.1, and the remaining things I'll set them as 2 3. So to this let me add lines x comma y1 color equal to red. So this is how the 1 beta is going to come out. You could see here there is some probability. So the beta is coming out to be like this, but the 1 beta is coming out more like this, right? So there is a small deviation that we are seeing within the beta as well as 1 beta, because after the value of x, after a certain point, we are seeing that the value of you could see here at x equal to lesser values, you could see that the peak is slightly narrowing down compared to your d beta function itself. The same thing you could create r beta as well as r beta 1 modified, and you could see how the random values are slightly changing. So these are typically your mixed distributions, wherein in some cases it is following a beta distribution, whereas in some other cases it is not following. It is typically the density, the distribution function is having a value of 1 itself from there onward. So the density function actually becomes 0 from that particular point onwards. So there is only 1 minus p probability that it follows a beta distribution, and after that it is going to become 0 all the way. So these are some of the kinds of instances that we really need to look at when we are plotting the distributions, especially the mixed distributions. We can very well get not just the density function, we can also get the distribution functions as well created. We can get the p beta om function, which also goes the same way. When you are going with p beta, instead of simply taking it as x equal to 1, we'll take it as greater than or equal to 1. So the probability of q value greater than or equal to 1 is what we will take, because the cumulative distribution becomes equal to 1 for all values of x greater than or equal to 1. So that's how we understand the mixed type distribution. Then the other concept that we need to be comfortable here is mixing two distributions. So in some cases, my data could be a mixture of two distributions. So there is a p probability chance that it is following a gamma distribution, and 1 minus p probability that it is following a normal distribution. So it is typically randomly drawing a distribution among a finite set of distribution. I'm mixing. So I can mix two normal distributions. So this is a normal distribution with mean m1 and standard deviation s1. This is a normal distribution with mean m2, standard deviation s2. So this is a mixture. So there is a p probability that it follows a normal distribution with mean m1 and standard deviation s1, and there is a 1 minus p probability that it follows a normal distribution with mean m2 and standard deviation n2. Similarly, I can have some probability that it follows a gamma distribution. So especially for claims, I can try this kind of mechanism. So there is some probability that it follows a light-tailed gamma distribution, and some probability that it follows a heavy-tailed Pareto distribution. So I can very well create a mixture distribution like this. I can create a mixture distribution like D mix gam par from the existing. So I am taking two different distributions. I have to just give the probabilities associated with each one of them. So let's say it's better that we use D gam par D mix distribution, where we are using gamma and Pareto together. I can very well use a mixture of gamma and Pareto distribution. So let's call it as D gam par, or probably D gamma Pareto. That's the name of the function that I want to create. So I'm taking a function of x and prob is required because I have some kind of probabilities. Now I require two parameters for gamma distribution, the shape and the rate parameters, and similarly I require two parameters for the Pareto distribution. So that's where we can give some names, right? Probably let's first take we'll call them A, B, C, D. So the first A and B are typically the two parameters for the gamma distribution. C and D are the two parameters for the Pareto distribution. We'll call it accordingly. So we'll take, okay, there is a probability, P probability chance that it follows a gamma distribution. So let's call it as D gamma and X A comma B. So these are the parameters of this gamma distribution. And we have 1 minus P probability, which is 1 minus prob, and this is D Pareto, right? It follows a density function associated with a Pareto where I am taking X comma C comma D. So this is how I generate the D gamma Pareto function. Similarly, if I have to generate the P gamma Pareto for this, right, I can very well generate the P gamma Pareto for this again with the same function of, we will use, if I have to generate the P gamma Pareto again, I am using function of X prob A comma B comma C comma D. Even here I will simply take it as prob multiplied by P gamma of X comma A comma B plus 1 minus P 1 minus prob multiplied by P Pareto X comma C comma D. So I can very well generate the P gamma, which is now a mixture distribution is being created, where there is some chance that it becomes a Pareto distribution and some chance that it is following a gamma distribution. So these kind of distributions are typically called as the mixture distribution. Now using them I can very well, now you could see here, let's try out, right? So I'll take my Y as, so let's take X. X is coming out as sequence from 0 to 10, increment by 0.01. Y, let me take it as D gamma Pareto X. Prob, let me take it as 0.25. There's a 0.25 chance that it is, or probably let me say 0.75. There is a 75% chance that it follows a gamma distribution, 25% that it follows a Pareto distribution, right? So the gamma distribution is having parameters 2, 3, Pareto distribution is also having the parameters 2, 3. D Pareto, there are some ends that NANs are produced. Let's see why. Now based on this I can very well go ahead in terms of generating plot of X comma Y, wherein I am setting the type equal to L. A line chart is what I want to plot. And this is how my D gamma Pareto is coming out. But let's say on the other hand, if I am generating Y1, which is purely a gamma. So if I am saying D gamma of X comma 2 comma 3, and let me add the lines X comma Y1 color equal to red. So now here I could see a completely different set of graph out here, which is purely a gamma, slightly lesser tail, whereas a gamma and Pareto mixture is showing a slightly fatter tail out here. right? You could see a slightly fatter tail in case of the black compared to that of the red. So that's the kind of understanding that we can have if we are generating a mixture distribution following two different kinds of distributions altogether. Right, so you can mix any kind of distributions in this particular mechanism. You give a probability that it follows some distribution, another probability that it follows some other distribution. Both of them can very well be mixed in R by creating a D function for it, by creating a P function for it separately, which is just by giving all the uh, both the both the individual density functions parameters can be given as the input, and the same can very well be generated. Now, one more important point before we wrap up: some kind of distributions, especially in the mixture distributions, we have something called the phase by phase type distributions, especially when we are talking about a vector of probabilities. So especially if you remember uh, the scenarios, the time to absorption of a Markov jump process. So from this state up to this particular state, and we are talking about the initial probabilities where a generator matrix is being provided. So we have a generator matrix or the intensity matrix like this, and based on that, if I want to find out what is the time to absorption in a particular state in a Markov jump process, I can very well use the phase type distribution. And even the phase type distributions, especially the Erlang distribution, is there as a part of the Actuar package. You can very well explore that kind of phase type distributions also as a part of the Actuar package. So that's where the richness of the Actuar package comes up. Not just the very common kind of distribution, but most heavily used distributions across the actuarial world, they are present as a part of this Actuar package. So we can very well look at reading through the documentation associated with that package and getting and doing some kind of experimentation on that package to get some kind of good hold associated with different kinds of distributions. So where and when required, we would be taking up those specific distributions, working them on the data, and try to look at the results coming out of these distributions for actuarial modeling purposes. So this is what I wanted to look at as a part of this session. These are the various elements that we have already covered, right? If you have any further queries regarding the same, please feel free to get in touch with me by giving me a call on the number that I have provided below, or you can even send in an email at the email address specified below. Thanks a lot for listening to this session.